I just forgot the headset. So again, the sound is not going to be real great. So I'll go ahead and record it. Chapter 4 is on work and energy. Let me ask y'all a question first, actually, before we get started on this. How many of y'all have clickers? You know what clickers are? How many of you just raise your hand? Or how many don't have clickers? Yeah, we're not going to get into this class, but I'm just curious for further years. Do you get clickers for your athletic training classes, or do you get them for other classes? For biology? Okay. How many of y'all feel if I use clickers in class? I made it part of your grade. I can't type stuff. Is that okay? Yeah, there'll be more functional points. We're not going to use this in this class. I'm just curious how we're doing it in the future. I didn't do it for that. I didn't want to make y'all buy something just to like that. So if you're using it in other classes, that's generally true for you. How many of you know that to not be true for? Raise your hand. Cool. All right, well, I can just use you for stuff, and then we'll be clear. Okay? Okay. I think you can mention it too and tell us that. All right. So chapter 4 is on work, energy, and power. So first, we just want to ask our question, what is work? And there are a lot of different definitions for work, right? Like it can be a job, it can be stuff that you're doing around the house. But in physics, when we talk about work, we're going to say that the work that an object does is equal to the force times the displacement. So that has a particular quantitative meaning, the force times the displacement. In particular, this displacement is in the direction of the force. All right, so the work would equal F, the force times the displacement. And if I were to draw them as vector quantities, the force would be in this direction, and the displacement would be in the same direction. We'll work through some examples, and I'll show you the differences if the opposing directions are perpendicular to one another in just a bit. Also related to work, very closely related to work, is energy. In fact, we'll equate the two in this chapter. What is energy? There are all types of energy, but in a general sense, we're going to call energy the ability to do work. And all types of energy can be defined by this. It's just the ability to do work, the ability to provide a force over a displacement, the ability to do work. And that applies to food energy, to chemical energy, thermal energy. All types of energy are just the ability to do work. So this has many different forms. Has many different forms. Can I go to the next page? Okay. I'll give y'all just a second. Okay. All different forms. Primarily in this chapter, we'll deal with kinetic energy, that's the energy of motion. I'll write that down in a second. But kinetic energy. We'll also deal with potential energy, in particular gravitational potential energy. That's when an object has the potential for motion. There's chemical, there's thermal, there's nuclear energy, there's electrical energy. So it has lots of different forms. All right, there's kinetic. That's associated with what? With motion, yeah, with motion. There's potential energy. Within potential, we have two different types that we'll talk about. Gravitational potential and also elastic potential. There are other types of potential energy, like chemical energy is sort of a type of potential energy. Let's see, there's also thermal, chemical, nuclear, electric. The whole next chapter will be dealt with thermal energy. Electrical energy, we'll do that in a later chapter. nuclear, chemical. Right? And all of these things are related to the ability to do work. The unit for work and for energy, the SI unit, is, remember, work is equal to force times displacement. What's the unit for force? It's the Newton, right? So the unit for force is Newton, and the SI unit for displacement, of course, is meters. So newtons times meters. So the unit is 1 Newton meter. And sometimes you'll see it written as that, but usually when you see work, you'll see it as a joule. So the SI unit is the joule, and it's the equivalent of a Newton meter. All right? So it's a joule. The abbreviation for this is a capital J. It's a person's name. It was named after James Joule, who studied energy. You don't need to know this name, okay? So if it doesn't interest you, don't write it down. James Joule, and 1818 to 1889 is when he lived. So not that long ago, really. All right. And just show you some simple calculations where you can, if you're moving an object over a certain distance, we can calculate the amount of energy required to move it that distance, or the amount of work required. I'm going to use the terms energy and work kind of interchangeably, and I'll give that in a more formal way in just a little bit. We'll call it the WorkEnergy Theorem. Let's say that I have a block, piece of furniture, whatever. All right, and I need to push it across the floor. I want to push it from here over to here. Let's say that this distance is equal to 2 meters. And in order to push this, I have to exert a force. And that force is going to be equal to 10 newtons. So if I want to know the amount of work, I just say the force times the distance. That's going to be 10 newtons times 2 meters. And that's equal to 20 Newton meters, or 20 joules of work. Right. What if I have a situation like this? Let's say instead of pushing an object across the floor, let's say that I'm holding an object, a block. Now my arms have to exert a certain force in order to hold that object up, correct? Just to hold something requires your muscles to engage and to exert a force. So I'm applying a certain force. Let's say it's 10 newtons. All right? Say it's this book, for example. I'm applying a force like this. How much work am I doing? I'm not doing anything at all, right? Because my distance that I'm traveling is nothing. All right, so if my displacement here is 0, even though I'm exerting a force, I would say that my work is equal to the force times the displacement, which is equal to 10 newtons times 0 meters, which is equal to 0 joules. All right? What if I have this block, or whatever, this book. I have to exert a force equal to 10 newtons in this direction. And then I'm going to walk over here at a constant velocity. All right, that's going to mean that my force in this direction is equal to 0, right? Because constant velocity means that my acceleration is 0. And if I have 0 acceleration, that means I have 0 force. So it's just like I'm walking across here, and I'm not exerting any forces in this direction, moving at a constant speed. Well, let's say that I move 2 meters. What is my work that is exerted? I'll call this F1, I'll call this F2. the work that's exerted by F2. What's the work exerted by that second force? That is the force that's causing me to move across the stage. Like we said, there's no force at all, right? Because I'm not accelerating. So what's the work that's done by that force? It's going to be 0, right? So the force done by that, the work done by that force is 0. It's going to be F2 times my displacement, which is 0, because F2 is equal to 0. All right. What's my work done by F1? This is really the important point. So work done by F1? It's going to be 0 as well. The reason is that even though I have a displacement of 2 meters and I have a force of 10 newtons, they're perpendicular to one another. So it's very important that when you're calculating the work, that the force and the displacement are in the same direction. Right? Or at least parallel or anti-parallel to one another. Either in the same direction or in opposite direction. I'll show you some examples. Yeah, the work done by F1, that force that I'm holding up this book of 10 newtons, that work is equal to 0 because the displacement is 90 degrees to the force. Let me write it up on the board, okay? They're not in the same direction. Right, yeah, I'm just holding it. I'm holding it, but I'm walking across at a constant velocity. Right, so I'm moving it, but my force isn't moving it. My force is just holding it here. All right, so F1, I'll call this D, and D are not in the same direction. So the work done by F1 equals 0. Excuse me, the work done by F1 equals 0. So in equation form, I'd write that as work done by F1 is equal to F1 times D. I'll call this D1. All right, but that's going to be equal to 10 newtons times 0 meters. Because D1 would be the amount of distance that it travels in this direction, and that's equal to 0. The point is, it goes back to that definition of work, that the force and the displacement have to be in the same direction. Or we'll see an example later where it has to be in opposite directions. But in that case, we get a negative work, like for example with friction. We're actually taking energy away from the object. All right, why don't y'all try this? I go down from here? Y'all just a second. Did y'all hear about the guy? The entire left side of his body got cut off. Have you heard that guy? He's all right. He's all right. That's a good one, isn't it? All right. Okay. How much work is done? All right. How much work is done in lifting a 10-kilogram sack two meters from the floor to table? All right, I'll give you some options even. This may be a good test question, actually. Let's see. Is it 20 joules, 200 joules, 5 joules, or 0 joules? how much work is done in lifting a 10 kilogram sack 2 meters from floor to table? 20, 200, 5, or 0 joules? On the other side. You can answer this. And the work is force times displacement. You say it's the vertical force. What's your force? This is the force. Right, so it's the force due to gravity. I give you the mass, right? So the mass is 10 kilograms. And so the force at the plate is the gravitational force. But you have to exert a force that's equal to the gravitational force in order to lift it. So it's 10 kilograms times 10 meters per second squared. So that force is 100. So what's the work? All right, so the work is 200 joules. Now I'm lifting this object. I have to exert a force equal to the weight of the object. That's 10 kilograms times the acceleration due to gravity, which is 10 meters per second squared. So that's equal to 100 newtons. And I'm moving it over a distance of 2 meters. That's my distance. And so my work is equal to force times distance. That's 100 newtons times 2 meters is 200 joules. And so it would be B, be the right answer. All right? Y'all are okay with that, maybe? No, fairly straightforward? Okay. You can see a question like this. You could also see a question like the previous one where I have a force that's being exerted, but the displacement is not in the direction of the force. And in those cases, your energy or your work done is 0. All right. Let's look at energy, and we'll come back to work because work and energy are closely related. Energy is the ability to do work. I think I've already said this, but I'll write it again. It's the ability to do work done by a system. By a system. Removes energy from the system. Work done on a system. Increases the energy of the system. All right. For example, let me show you. Let's say, let me show you one example here. A toy car, like one of those little wind-up toy cars. Y'all seen those before? I have a wind-up toy car. I have a key coming out of it. And I wind it up. What am I doing to the energy of that system? The system being the car. Am I increasing or decreasing the energy of the system as I wind up that car? What is it? I'm increasing the energy of the system. I'm doing work on it. I'm applying a force over a certain distance, and I'm increasing the energy of that car. Okay? And then, what if the system does work? If I have So if I wind up the car, I increase, or excuse me, I do work on the car. Or the car is my system. I'm doing work on the car. That's like doing work on a system. So I increase its energy. All right? If I let the car go, it does work. The car does work. So the energy of the system decreases. So the car's energy decreases. All right. So that's the difference. When I talk about a system, I talk about the energy that's held by that system. In this case, the system is this car. If I wind it up, I increase the energy that's held within that system. If I let it go, then the energy of that system is spent, and it's used to make the car move. You can see this also. I have a ball. Right, if I move it, the way that I can increase the energy of the ball, the way I can increase the energy of the ball is just to move it up, right? If I move it from here to here, then that increases the energy of the ball. And how can I release that energy, right? How can I cause the ball to do work? And in that case, the ball is losing energy. Okay? You understand the difference between work being done on a system and work being done by a system? You'll see a couple of homework questions, especially in the questions part of the homework, that's related to this, to test this further. When you do work on a system, you increase its energy. When the work is done by a system, you decrease its energy. All right. Let's look at different types of energy. The two main types of energy that we'll look at are kinetic energy and potential energy. Kinetic energy is fairly interesting, just the history of it. Kinetic energy, which I'll abbreviate as a KE. Sometimes, like if you're taking standardized tests, you'll see it just as a K. But kinetic energy, I'll abbreviate KE. Do y'all take any standardized tests for graduate school and what have you? Like the MCAT or something similar? Yeah? For PA school, you take is it that the PCAT? The GRE? Yeah. All right, so for kinetic energy, this is the energy of motion. We can calculate the kinetic energy. It's equal to 1/2 mv squared. All right, so I had this proportionality between kinetic energy and the square of the speed. You know, for a long time, people didn't believe that this was true. That wasn't until, let me see, the 1700s? I don't have the date, but it was somewhere in the 1700s, I think. Before that time, when they were able to show this experimentally, that the energy of an object is equal to its mean squared, they typically didn't believe that numbers could be squared and describe physical systems. Do you have any idea why? Well, they thought square numbers were a form of witchcraft, and that squared numbers in and of themselves were evil and had some evil connotation to them, which was kind of silly, right? I believe in it, because if numbers are square, that's not evil in any way. But why would it be silly for people back in the 18th century to think that square numbers were evil? How was it that they used square numbers a lot? What did they do? People in the 18th century farmers. They what? They were farmers. she did this experiment, which was pretty groundbreaking for the time, because they didn't think that kinetic energy could be proportional to the square of the velocity. What she did is she took some clay, and I say if you know kids, this is a good science experiment. It has a nice historical context, and it's fairly simple. But she took some clay, and she took a ball, and she dropped it so that when it fell into the clay, it had a speed v, and it made an indentation in the clay, and she measured the height of the indentation. And then she took a ball and she dropped it from a higher height. And at that time they had these equations of motion, Galileo and Newton came up with. And so she knew how high to drop the ball so that when it reached the bottom, it would have a velocity that was twice the velocity of the first ball. All right? And so if you believe that the kinetic energy isn't proportional to the square of the velocity, instead that the kinetic energy is just proportional to the velocity and not the square, how deep should this indentation be when it goes here? How much deeper than this one? If it's going twice the speed, it's going to have how much more, twice as much energy, and so it's going to drop down twice as much. But how much deeper did you find that it dropped into the clay? A factor of 4, right? Because if you increase your speed by a factor of 2, 2 squared is equal to 4. So it increases the kinetic energy by a factor of 4, and you get an indentation in the clay that is 4 times as deep. So she found that this was 4H. And that was a very groundbreaking experiment to show that kinetic energy was proportional to the square of the velocity. And then she also, in very rigorous scientific measurement, she also found that it's proportional to the mass as well. That was sort of known at the time, that if you drop a heavier mass into the clay, it would make a deeper indentation. But she showed that as well. It's also interesting because, well, she was a woman, and there weren't many women scientists in the 18th century, and she was just sort of an interesting character. I have a little clip about her. A person that wrote a book about her does an interview. So you're not responsible for the information, but it's fairly interesting. You do need to know her name, though. Her name is Emily de Châtelet. I think she was French. De Châtelet. I think I spelled that correctly. Yeah. All right, I'm going to come away from this, then I'll start the clip. All right, give me just a second.
He was a revolutionary philosopher and critic. She was a brilliant young aristocrat, and their love affair would capture the spirit of the Enlightenment. But could be the plot for a period drama actually played out in real life.
The thinker Voltaire found a soulmate in Emily de Châtelet, pioneering scientist and intellectual. Author David Bodanis tells their tale and her story in the new book, Passionate Minds. Born in 1706, Emily de Châtelet was a bookworm when the king's own daughters were illiterate. She was a math whiz. And when she was sent to Versailles to find a suitable husband, which she eventually did, Bodanis writes that the 16-year-old hit on a way to fend off lascivious courtiers. She challenged one to a duel.
They went to one of the big buildings at Versailles, and she started taking her clothes off. Not all of them. She saw just the equivalent of petticoat wear. And turned out she was in a little bit of a tomboy as a child. And the doctor had given her fencing lessons and horse riding, and she had been allowed to climb trees and stuff. So she didn't lose her, she didn't kill the guy, but she didn't lose either, so did the girl. And after that, she put down her sword, lifted up Descartes' analytic geometry, walked back outside, and the guys left her alone.
Voltaire said, Voltaire, this man that she was engaged with, he said that Châtelet was, quote, a great man whose only fault was being a woman. A great man whose only fault was being a woman. So things have changed a lot, I think, right? Things have changed since the 18th century. Let's see. All Let's do a couple of examples. Oh no, we'll come back to this in just a moment. Sorry. Show you something else. We've already said this, but I want to make this more formal, and you have a couple of homework questions that are like this, that use this. The WorkEnergy Theorem. This whole idea that if you do work on an object, you change its energy. We're going to write this as an equation, that the work is equal to the change in energy, that if I do work on an object, I change its energy. And in particular, I will often, if I do work on an object, change its kinetic energy. And I'll show you some examples we'll work through. It's not always that you change its kinetic energy. Like for example, if I take an object and I move it from a certain height up to a higher height, I've changed its energy, but not its kinetic energy. I've changed what we call its potential energy. And we're going to work through some examples where we see when we do work on an object, like pushing something, that we change its energy. And this is called the WorkEnergy Theorem. As I said, there are several homework problems, but we're going to work through some that are very similar here. How much work must be done to accelerate a 1,000-kilogram car, to accelerate a 1,000-kilogram car from 0 to 10 meters per second. From 0 to 10 meters per second. All right, you need to start with this. I'll give you some options like I did before. Don't forget that kinetic energy, I said this on the previous page, but it's equal to 1/2 of the mass times the speed squared. And I want to know how much work is done to accelerate a 1,000-kilogram car from 0 to 10 meters per second. I'll give you these options. 10,000 joules, 100,000 joules, 500,000 joules, or 50,000 joules. Which is it? 10,000, 100,000, 500,000, 50,000. I want to accelerate a car from 0 to 10 meters per second. Let's do the example with that question, okay? How much work is required to accelerate a car from 0 to 10 meters per second? Okay, really not. That's fine. The initial velocity is 0, and the final velocity is 10 meters per second. Any other answers on it? What? Yeah. Answer clear? Anybody? What do you think? That's right. The answer is B, right? 50,000. If I want to know the work, I just look at the change in kinetic energy. The work is equal to the change in kinetic energy. That's going to be the final kinetic energy minus the initial kinetic energy. That's 1/2 mvf squared minus 1/2 mvi squared. Alright, this whole thing right here is 0 because it's initially at rest, it has no kinetic energy, and so it's just 1/2 of the mass, which is 1,000 kilograms, times 10 meters per second squared. Alright, and that's equal to 50,000 joules. Let's do another one. In this class we don't spend a whole lot of time on kinematics. Like the kinematics problems that we do are fairly simple, but they can get fairly complicated. But when you use this whole WorkEnergy theorem, it makes kinematics problems exceedingly easier than they would be otherwise. And actually it was when Newton first developed the laws of motion, he developed them in terms of energy and momentum, which we'll get to later. Alright, let's say a baseball player, another example, baseball player exerts a force of 200 newtons for a distance of 5 meters That's a long distance, that'd be like 15 feet, but we'll just still use it, that's what I wrote. For a distance of 5 meters on a ball with a mass of 1 kilogram. What is its final velocity? Alright, I'm going to write these little equations over here. Work is equal to force times displacement. My work is equal to my change in kinetic energy, and kinetic energy is equal to 1/2 mv squared. See, I'll give you all a few options here. Is it 5 meters per second, 2,000 meters per second, 45 meters per second, or D, 30 meters per second? If I do work on an object, I increase its kinetic energy. Just a few minutes and I'll work it out on the board. You first want to find the work that's done on the object, then that's going to equal the change in kinetic energy. You're going to set that equal to the kinetic energy. And you're going to have all these equations as well. What's the work that's done on the object? Right, 5 times 200, 1,000 joules. Okay, I think somebody already said something about delta H. Let me just show you. I think I already said the second one. Yeah, let me show you. Alright, so my work is equal to the force times displacement. the work that the baseball player does on the ball, and he exerts 200 newtons, and he has like 8-foot long arms, so he does it over 5 meters. All right, so that's 1,000 joules. So he increases the energy of the ball by 1,000 joules. So I can say that that work is equal to my kinetic energy. So I say 1,000 joules equals 1/2 times the mass. The mass is 1 kilogram times the velocity squared. And I want to find that velocity squared. All right, so I'm going to divide both sides by 1/2 times 1, 1/2 times 1. That cancels out this, all right, and gives me, if I divide 1,000 by 1/2, that's 2,000, and then that's equal to v squared. How do I get rid of that v squared? I square root it. The square root of v squared, the square root of 2,000, and I get 45 is equal to v. That's the answer. It's about 100 miles an hour. 45 meters per second, about 100 miles an hour. That's a good number to keep in your mind. The next time you're out driving at 100 miles an hour, you look out over at your friend, man, I'm going 45 meters. Okay, David. Right. No, it's 2,000. So if I take that half and I flip it, I think on the numerator, it becomes 2. 1 over a half, that's 2, right? You can just make it a point. All right. That's probably not as difficult as the algebra with it. Okay. But there is some level of work that you do. So if you have trouble with it, don't come see me. Okay, I can really help you out with it. So everyone okay with it? Work is energy. When you do work on an object, you're going to increase its energy. All right. Let's look now at potential energy. Actually, I have a little clip. Let's go ahead and watch that. This is about the circus. I think I've showed the circus clip before. And it's just about energy and how they use energy in the circus. I think the Nichols cheerleaders should get one of those bars. Don't you think? Wouldn't that be super cool? Way up in the air. All right. Where was I? All right, so potential energy. He mentioned potential energy. And there are several different types of potential energy, but largely we'll deal with gravitational potential. This is the energy due to an object's shape, position, or chemical makeup. Shape, position, or chemical makeup. All right, so for example, we have elastic potential energy. That's like in the bar. When the bar would bend, it would build up its elastic potential energy because it is deformed and wanted to return back to its original shape. We see elastic potential energy also in springs, for example, in our bodies as well, elastic potential energy. Gravitational potential energy. That's like, for example, the ball. Like if I take a ball and I move it up away from the earth, I've increased its potential for motion. Just like a dent in the floor. That's 4 times as much as if I dropped it from right here. All right, so gravitational potential energy and chemical potential energy. The chemical makeup, like for example, the fuel in your car, the food that you eat has chemical potential energy that's unleashed by your body. So we have elastic, gravitational, and chemical. In this chapter, we're going to deal primarily with gravitational and then also with chemical. We'll get into like food energy and what have you. The gravitational potential energy. You don't need to know this little derivation, but it's fairly simple, so I'm going to show it to you. The work done by a gravitational force is equal to the force times the displacement. Actually, I'm going to change this and make this an h. So that means that if I move an object from here up to here, that's a height h. And the force that I'm exerting on it is here. That force is equal to the gravitational force, which is just equal to m times g times h. So the work when I move an object from here up to a height h is equal to the weight of that object times the height that I change it by. And so the amount of potential energy then is also equal to this. So the gravitational potential energy, which I'm going to call PE, is equal to m times g times h. My gravitational potential is m times g times h. All right, so for example, let's say how much energy or how much work is required to lift a 25 kilogram child onto a table 0.5 meters high. All right, how much work? And then so also this is going to be what is its potential energy. All right, I'll give you some options here. Is it 13 joules, 125 joules, or 50 joules? Which is it? How much work is required to lift a 25 kilogram kid onto a table that's half a meter high? At it two different ways. The work is force times displacement. All right, the force that I'm exerting is the weight times the displacement. So that's 25 kilograms times 10 meters per second squared. That's the acceleration due to gravity times 0.5 meters, and that's just equal to 125 joules. So the answer is B. All right, or you can think of it in terms of gravitational potential energy, which is m times g times h. All right, let's see here. All right, we'll come back to this in just a bit next time, but let me go into something else. So, but we'll come back to gravitational potential energy, and you'll see it in your homework as well. Thermal energy, which we'll have a whole chapter devoted to thermal energy and calorimetry and stuff like that next next chapter. I'm also going to call this internal energy, thermal or internal. It's the energy that's associated with the random kinetic energy, or with the random motions of atoms and molecules. All right, so within any substance, the atoms or the molecules are moving, and that's actually what causes the heat. Because when those atoms or molecules move, they generate a amount of heat. They have a certain amount of energy, and then that shuts on into the thermal energy. Y'all take chemistry? What part of chemistry? Some of y'all take chemistry. But have y'all ever been required to take chemistry? You what? You just take this instead of chemistry, or well, this one. Is it? Anyway, if you were in chemistry, you probably talked about this. In fact, all of classical thermodynamics is really just doing what we've been doing with kinetic energy and applying it to big samples of gas. And it's really not much more complicated than looking at the kinetic energy of atoms and molecules. Thermal energy often arises from the friction of two surfaces. Right, what happens if you rub your hands together? What happens to your hands? They get really hot. Yeah, you create energy. The friction between your hands causes your hands to warm up, and that creates thermal energy. Often arises from the friction between two surfaces. This, by the way, I didn't know this, but I read it in our book. This is why massage therapists use oil to decrease the amount of energy that's lost to thermal. And I guess it feels good too. All right. We generally consider thermal energy as lost energy. Because you're not going to get it back. So you can probably think of lots of examples where this is true. Where anytime that you're producing thermal energy, that energy is lost forever. Like if I rub my hands together, it heats up my hands for just a second, but then that thermal energy, it just sort of goes up to the world and goes away. And moves on to other systems. Or in your car, for example, when the engine gets really hot, that energy is basically useless. It doesn't go into moving your car forward, it's just lost as thermal energy. Right? So there's a lot of work that's done to try to decrease that amount of thermal energy that's lost. Can y'all think of any other examples? I know y'all get hands people up here. Any other examples? It's a long time to sit in your chair, so I want to cover one more thing, about 3 more minutes, okay? And then we'll go. Just chemical energy. I have a couple of things to say. And this will apply to some of your homework problems, and next time we'll look at chemical energy. It's energy stored in chemicals or molecular bonds. energy stored in chemicals or molecular bonds. Food energy, which we'll get into next time, is a type of chemical energy. This food energy has to be converted to work. That is, doing a force over a certain displacement, or the energy is converted, the food energy is converted to what? Don't know? If you don't use the food energy, it's converted into fat to be stored and saved for later. And we'll talk about food energy and kilocalories and calories and all that jazz. So one last thing, the energy content of food is given in kilocalories. Kilocalories. The abbreviation for this is KCAL. That's the same as our food calories. So the calories that's listed on food items is actually in thousands of calories, and it's abbreviated with a capital C for a kilocalorie. And this is equivalent to 4,186 joules. You'll have that number. You'll need it for the exam most likely, but you'll have it on the exam, that a kilocalorie is equal to about 4,000 joules. All right? I think we'll stop there. We'll come back with an example next time dealing with kilocalories. I have a few proposals, and if you didn't get the quiz last couple times, bring this. I made it for you, Laura, Deshaun, Hillary, Marion, Renee, Nikki Boudreaux, Candace Boudreaux, and Justin Daniel. Otherwise, don't forget there, okay? Let me know your quiz. If you didn't get your quiz, come see me. I still have a few left over.